This is the second part of the first lesson on chemical basics and basic atomic structure. In the previous video, we left off with determining the atomic number, mass number, protons, neutrons, and electrons in an atom. What we want to do now is we want to get a sense of what an atomic mass is and how we calculate it. So first of all, we want to understand that the natural abundances of isotopes are not equal. And what we mean by that is this. If we look at an example, for example, potassium. Potassium has 3 naturally occurring isotopes. However, they don't occur equally, meaning they're not all 33%. So potassium 39 accounts for by far the largest portion of these at 93.26% of all potassium atoms. And then we have potassium 40, which accounts for only 1/100%, and potassium 41 makes up the remainder. Now these aren't numbers that you would need to remember or anything. This is just an example of what we mean by the abundances not being equal. Now until recently, it was thought that these abundances were a constant for any source of the element in nature. However, in the last 5 to 10 years, it's been discovered that these percentages will vary, only slightly though. So it's not like we're talking about 93.26% for one source and 95% for another and 90% for even another source. We're talking tiny fractions of percentages difference, but still it is a difference. What we also need to get a sense of is what sort of unit we use to measure the mass of these atoms. And that unit is called the atomic mass unit, or otherwise known as AMU. And the reason we need the AMU is that we need a mass for these super tiny masses. We're talking about particles that weigh way less than even a gram, which is not a very large mass in the grand scheme of things. But still, it's way too large to measure the mass of an atom. So we need the atomic mass unit. The atomic mass unit, or the AMU, it is defined as 1/12 the mass of a carbon-12 atom. In other words, what we're saying is the carbon-12 atom has the mass of exactly 12 AMUs. Okay, there's no ifs, ands, or buts. That's how the AMU is defined. That carbon-12's mass is exactly 12 AMUs. In other words, we could write it as 12.000000 forever and ever if we wanted to. Every other atom of every other isotope is measured relative to the carbon-12. So for example, if an atom is twice the mass of carbon-12, its mass would be 24 AMUs. This leads us to our definition for atomic mass. Atomic mass is the weighted average mass of the stable isotopes of an element. Note the term weighted. This will be a major topic of discussion for the rest of this video here. The weighted average mass of the stable isotopes of an element. Now this number is not a whole number. If you look on the periodic table, you will see atomic masses for elements listed, and you will see that they are not whole numbers. Another important point is that these are found on the periodic table. So let's look at an example of how we find a weighted average mass. So here's our example. It has nothing to do with atoms, but instead a football team. Total football team is made up of 35% linemen, which are 200 pounds each, 60% skill players, which are 175 pounds each, and 5% kickers, who weigh 140 pounds each. What is the average weight of a single player on the team? Now what we can't do is we can't simply find just the regular, or what you might call the straight average of those 3 weights. We can't just add up 200, 175, 140 pounds and divide by 3. And in that case it would be 172. Ask yourself, why not? Well, if you answer that question because there aren't an equal number of each position, you're correct. We have to account for the fact that 35% are linemen, 60% are skill players, and 5% are kickers. Because by just finding the straight average, we're saying that they all count equally towards the average, but they don't, because they aren't distributed equally. So we must find the weighted average. So here's how we do that. What we do is we take the abundance of each position. Notice here, 35% linemen. We turn that into what we call the relative abundance, or the decimal form of the percent. So 35% is 0.35, and we multiply by the value. And for the linemen, they weigh 200 pounds apiece. And then we add that for each position. So the skill players, they make up 60%, or 0.60, and times their weight of 175, and then 0.05 for 5%, times 140 for the kickers. And we take those numbers, we multiply them, and then we just add them together. So the weighted average is 182. Note when we find a weighted average, there is no division by the number of numbers here, not like a regular average. So I'm not going to take 182 and divide it by 3 because there's three values there. That doesn't exist in weighted average. So let's look at how this applies to calculating an atomic mass. So here's an example. We're told chlorine has two stable isotopes, chlorine 35 and chlorine 37. And we're told use the data on the two isotopes below to determine the atomic mass of chlorine. Here's the data. So what we're going to be given here is the isotope, the actual mass, and the abundance of that isotope. So chlorine 35, its actual mass, meaning if we were to weigh a single atom of chlorine 35, it would have a mass of 34.969 AMUs, and its abundance is 75.78%. So it makes up 75.78% of all chlorine atoms. Chlorine 37, on the other hand, its actual mass is 36.966 AMUs, and it makes up the remaining 24.22% of chlorine atoms. So to find its atomic mass, we're just going to find the weighted average. Recall that means we're going to take the abundance of the isotope in relative abundance form or decimal form, and we're going to multiply by its actual mass, and then we'll just add those values up. So the atomic mass is simply the weighted average. So here we go. So we have 0.7578 being the abundance of chlorine 35 times its actual mass of 34.969 AMUs, and I add those two together. Now whenever you do this calculation, note we have multiplication and addition. So for your sig fig rules, remember you have to follow the multiplication rules first because that's the calculation that's occurring first, and it's a different rule with the addition. So we actually have to follow both rules. So when you multiply, remember our rule is number of sig figs. So here to start with, I have 4 sig figs in the abundance, I have 5 in the mass, so I get to keep 4 sig figs. So for the first one, it'll round to 26.50 AMUs. For the second one, it rounds to 8.953 AMUs. Again, both have 4 sig figs because the abundance in both has 4 sig figs, and that's the fewest number. Now, when we add and subtract, remember our rule is not number of sig figs, but it's decimal places, or precision. When I look at the first measurement, it is precise. So looking at the precision of these measurements, I need to round my answer here to the hundredths place. So when you plug this in, your calculator is going to tell you 35.453, but then we should round that to just 35.45 AMUs. One last note on this here, because this is an actual element, chlorine actually exists, to check your answer, just look at the periodic table and see how that checks out. If you look at your periodic table, you'll see that this is the listed atomic mass of chlorine. Another thing to do is this. If it wasn't a real element, or if you didn't have a periodic table in front of you, just ask yourself, does your answer make sense? Notice our abundances here. It's about 3 to 1 ratio of chlorine 35 to chlorine 37, approximately 75% to 25%. So that atomic mass should be weighted closer to the 35 than the 37, and that's actually what we have here. Notice it's about 35.5 roughly, which is about 3/4 of the way, if you will, closer to chlorine 35 than chlorine 37. So that does make sense for a weighted average for the atomic mass of chlorine. Alright, here's a practice problem. I want you to determine the atomic mass of the fictitious element iowanium using the isotopic data below. And here's the data. In this case, we have 3 isotopes. And just like before, you're going to find the weighted average mass of these isotopes. So pause the video, try it yourself, and see if you get it right. Alright, so you've had a chance to work the problem. And again, we're just going to find a weighted average mass of these isotopes. So we're going to take the abundance of each in relative abundance form or decimal form. So for the iowanium 313.29203, multiply by its actual mass, and then do that for each of the isotopes, and then you'll add them. So remember, for our multiplication, for your sig figs here, it looks like we'll have 5 sig figs for each of them because the abundances are all 5 sig figs, and you can see the values you get there. Then when you add them together, looking at precision, so it looks like we need to round that to the hundredths place. So when you plug that in, you should round that to 318.08 AMUs. Okay, so we have defined and calculated atomic mass. The other thing we need to be able to do with atomic mass is we need to be able to determine the percent abundance of isotopes. So essentially going the other way from calculating atomic mass. So here's what that would look like. So we're told the atomic mass of boron is 10.811 AMUs. Which actually you wouldn't even need to be told that because you can just look it up on the periodic table. Boron has two naturally occurring isotopes, boron 10 and boron 11, with masses of 10.013 AMUs and 11.009 AMUs, respectively. Determine the percent abundance of each isotope. So here's what we know. We know we have to find the abundance of boron 10 and boron 11. So I'm going to come up with a couple of symbols or variables. We're going to say X is the abundance of boron 10 and Y is the abundance of boron 11. I know what the atomic mass is. So thinking about the equation that we have seen for calculating an atomic mass, I know the atomic mass is the actual mass of the atom times the abundance in decimal form, and then we add those together. So I know that 10.013 AMUs times the abundance of boron 10 plus 11.009 AMUs times the abundance of Y equals the atomic mass of 10.811 AMUs. Now if you look at this equation and you think about algebra class that you've had before, you'll recognize we have a little bit of a problem here. I have two unknowns or two variables, but I only have one equation. You've learned from algebra that if you have two unknowns, you have to have two equations to solve for them. So what's our second equation going to be? Well, it's actually very simple. Consider what X and Y are going to be and what they have to add up to. I know that the total abundance has to be 100%, or in decimal form, 1. So I know that X plus Y must equal 1 because they have to add to 100%. So if I solve for one of those, in this case I solve for X by just moving Y over, subtracting to the other side, I get X equals 1 minus Y. So I'm going to substitute that into the equation for X. So instead of 10.013 AMUs times X, I'm going to have 10.013 AMUs times 1 minus Y. Actually, my notes here, I say substitute for Y. I should say substitute for X, because that's what I solved it for. So I've just substituted in. Now notice here I only have one variable. I just have Y in this. So all I need to do is solve this equation for Y. So here's where all that algebra you've taken comes into play. So if I'm going to solve this for Y, the first thing I want to do is distribute my multiplication here in these parentheses on the left side. I'm going to distribute. So 10.013 AMUs times 1, that's just 10.013 AMUs. You see that here on the left. And then I take 10.013 AMUs times a negative Y, so that's minus 10.013 AMUs times Y. And the rest of the equation's unchanged. So I have plus 11.009 AMUs times Y, then equals 10.811 AMUs. At this point, I want to combine my like terms. Notice I have two terms in my equation that contain Y. So I can combine them. So I can just add them together algebraically. So I have a negative 10.013 plus an 11.009. And then I can subtract this 10.013 AMUs to the other side. So adding or combining my like terms, on my Y's, that's here on the left side, if I take the negative 10.013 AMUs and add the 11.009 AMUs times Y, that'll give me 0.996 AMUs times Y. And then subtracting my 10.013 AMUs to the right side, if I take 10.811 minus 10.013, that gives us 0.798 AMUs. So here's the equation we had before. Now to solve for Y, I just need to divide. Divide both sides by 0.996 AMUs, and that gives you Y equals 0.801. Now we're not quite done yet, but we've done the bulk of the problem. We still need a value for X. Now if you think about what we did initially, we had the equation of X equals 1 minus Y, just whenever we solved that equation for X. So plugging in my Y at 0.801, that gives us a value of 0.199 for X. Now at this point, all the math part is done. We just need to match these values up with the correct abundances and turn them into percentages. So notice X was my abundance for boron 10, Y was my abundance for boron 11. So boron 10, its percent abundance is 19.9%, again turning that back into a percent, and for boron 11, that's 80.1%. Now before we just call it good, let's make sure these numbers make sense. If you look at the atomic mass for boron, it's much closer to 11 than it is to 10. 10.811 being closer to 11 than 10. So much so that it's about 80% of the way towards boron 11, if you will. Notice boron's percent abundance is about 80%, boron's 10 is about 20%, so that checks out. So whenever you do these calculations, do ask yourself at the end, does my answer make sense? And if it does, then it's probably right. All right, one more question here concerning percent abundance. This one's a little more conceptual in nature. The question is this. Lithium has two stable isotopes, lithium-6 and lithium-7. Which isotope is more abundant? How do you know? And then it also says to approximate the abundance of each of the isotopes. Well, how would you know this if you're just told we have lithium-6 and lithium-7? Well, if you look at the periodic table, you will see the atomic mass of lithium is 6.94. So based on that, ask yourself, which one is more abundant? Is it lithium-6 or lithium-7? If you said lithium-7, you would be correct. And the reason for that is because the atomic mass of 6.94 is much closer to lithium-7 than it is to lithium-6, meaning there is more lithium-7 that exists. In fact, there's a lot more. So if you look at the answer here that I have, I say lithium-7 is more abundant. This is clear because the atomic mass of lithium of 6.94 AMUs is much closer to lithium-7 than a lithium-6 atom. And again, this is because this atomic mass is 6.94, we know is a weighted average. It's accounting for the fact that there is more lithium-7 than lithium-6. And then the second part of the question, approximate the abundance of each isotope. Ask yourself, how much more lithium-7 would there have to be than lithium-6 in order to get this atomic mass of 6.94 AMUs? And if you're thinking about this, and you don't need to do a calculation or anything, just approximate it. It's going to be at least 90%, 10%, because it's way closer to the lithium-7 than lithium-6. So very roughly, the abundance of lithium-10 is 10%, while the abundance of lithium-7 is 90%. If we wanted to do that calculation, we would need to look up the actual masses of those two isotopes. And if we did it, we would get somewhere close to 90% and 10%. All right, this concludes this lesson on atomic masses, calculating atomic masses and abundances. In the next lesson we'll be doing will be on basic periodic table stuff.